What is up, Precalculus? This is lesson 12.6. Today we're talking about the fundamental theorem of calculus. Before we get there, we need to do a few kind of pre-things before we get to that. And first off, these are actually the questions that I gave you from lesson 12.4. And then these are the answers that you're supposed to find. This isn't all of them, but this is most of them. And let's just look at these real quick. If this is our function, then we found the derivative of those functions, and we got this. So notice this 2 looks somewhat familiar. Hey, look, it's right there. It's negative 5. It's right here, and that kind of makes sense, at least for these two, because we talked about the derivative being the rate of change of those functions. And these are just linear functions, and so notice the rate of change would be the slope of those, so those perfectly make sense. Now these get a little bit more interesting. I have this negative 8 and an x, whereas up here I didn't have x's. Now I do have an x, and this negative 8 doesn't show up over here. But I'm kind of noticing maybe there's something going on here with this 2 and the negative 4. Is that how I get the negative 8? Let's see if that still holds. Here I have 10x. And look, that 10x is still, hey, 2 times 5 gives me that 10. And it looks like maybe something's going on with the exponents here. It was a 2 and now it's a 1. Let's keep going here. We'll have this 5x squared and that 10x, kind of like I had this 5x squared and I had 10x here. But now I also have a plus 5, which kind of comes from here, which is kind of similar to this up here, right? And then down here, notice there's a 1 out here in the 2 exponent, so 1 times 2. 2x, notice the exponent is reduced 1, and then that 2 goes there. So actually in lesson 12.4, they talked about this power rule for derivatives. And for some reason, books decide to put it in the same lesson. I never teach it in the same lesson because once you learn this, you never go through the process of what we did to find these. Because that process is a lot longer. Once you know this power rule, it's actually quite simple to find these. If you have some function, f of x, that is x to some n power, then the derivative is just actually going to be n times x to the n minus 1. And the same thing would apply true like if I have some constant times x to the n, the derivative would be the constant times n times x to the n minus 1. So even if you have a constant, like if you had a 5 in front of it, so you might take the exponent, multiply by the number in front, and reduce the exponent by 1. And that makes finding derivatives a whole lot faster and easier whenever they're in this form. Also, you can notice this is just for 1, but if you can take them individually, I can find the derivative of this one and then add it to the derivative of this one. That's why we were still able to do this one, even though we have 3 different terms. I can apply that rule to this one, and then to this one, and to this one, and just add those derivatives together. Because the derivative of this one would be 2 times 5, so it's 10, so 10x. The derivative of this would be 1 times 5. Reduce the exponent by 1, so it makes it 0, so it's just 5. And then this is like x to the 0th, I guess. So 0 times 5. But the derivative of a constant is always 0. So with that being said, we need to point out something real quick. Here are 2 functions, f and g. And let's find the derivative using that power rule that we just talked about. The derivative of this first one would be this 2 times the exponent, which is 2, and then x to the 2 minus 1. And then the derivative of the constant, so this would be plus 0. Or that would just be 4x to the first power. If we look at this next one here, exponent, so the 2 that's out in front, times the exponent, times x to the 2 minus 1. How fast is the constant changing? It's not. So that's just going to be plus 0. So it's going to be 4x. So notice here, the derivatives of both of these functions, both f and g, are 4x, even though my functions are different. And so that's because this constant, whenever you take the derivative of that, is different. Or the derivative of 5 and the derivative of negative 17 are both 0. So even though the functions are different, the derivatives, the rate of change, is the same. So what we're going to be working with today is actually what we call antiderivatives, where instead of if you were given something like this, can you find this? And so, and we actually use the integral symbol, which we've worked with some. You use integrals for finding area under a curve and also for finding antiderivatives. And so think about trying to do the opposite of the power rule. All right, we're going to add 1 to the exponent, and then we're going to divide by the new exponent. Because before we multiplied and subtracted, so now we're going to divide and add. And notice that is only works if this exponent is not equal to -1. In a future class, we'll talk about what is that if it is actually -1, but for today, the power rule only works if n is not equal to 1. And so all of them you'll be getting on your homework is going to be for n is not equal to 1. So we add 1 to the exponent, we divide by the new exponent, and then we add c. Now we just say plus c because we don't know what that constant is. That c stands for constant. It might be a 5, it might be a -7, we don't know, but we just know that there is, or that there could be a constant. It might be plus 0, but we're going to add on that plus c to make sure that to demonstrate that we know that the antiderivative of nothing is a constant. So we put that on there. Also, same idea if we have a number out in front of it. Same idea applies, we just multiply it back in afterwards. And same idea, we can take them individually. Like if we have more than one, we can take them individually, integrate each one of those, and then, or find the antiderivative of each one of those, and then we can do that. All right, so here we go. For number 10, this is, again, one of them off of your homework. Number 10, this is going to be, we're trying to find the antiderivative of this. It's going to be x to the 5 plus 1 over 5 plus 1 for this part right here. And we're going to have that -12 that we're going to multiply by that. So this constant goes right here. Exponent, I'm adding 1 to it, I'm dividing by the new exponent. Then for the next part, I'm going to say plus. It's going to be x to the 3 plus 1. I'm going to divide by that 3 plus 1. And we're going to have that 8, multiplying by it because that 8 comes out in front. And then, of course, we are not going to forget our plus c. Obviously, we want to simplify this down a little bit. So this is going to be x to the 6th over 6, and I'm multiplying by the -12, plus 8 times x to the 4th over 4, plus some constant. 4 reduces with 8, giving me 2x to the 4th. The 6 reduces with the 12, giving me -2x to the 6th. So this is the antiderivative of this. Notice if we were to take the derivative of this, we would get this. Let's do that here for number 11. Same idea here for this 18. I'm going to have 18 multiplied by x to the 6th over 6. I got that 6 because I said 5 plus 1 more. Divide by the new exponent. For this next one, I'm going to say plus 20 times x to the 3 plus 1, which is 4, over 4. Then for this one, I'm going to add 1 to the exponent right now that it's x to the 0th, so it's going to be plus 4 times x to the 0 plus 1, or 1, over 1. And then remember our plus c, plus some constant that we don't know what it is. Technically, I guess we should be saying that this one has a plus a c, This one has a plus a c, and this one has a plus c. But since it's some constant that we don't know what they are, we're just adding all of those mysterious plus c's together and putting it in here on the end. So let's go ahead and continue to simplify down here. 6 goes into that 1 time, into that 3 times. So it's going to be 3x to the 6th. Plus 4 goes into that 1 time, into that 5 times. Plus 5x to the 4th. Plus 4x plus a constant. Alright, and now the moment you guys have all been waiting for and begging to get to. You've been screaming this whole time, what is the fundamental theorem of calculus? And well, here it is. We worked with some of these, which was to find the area under the curve between 0 and 4, between -4 and -1. And we call this a definite integral. The ones we were talking about, other one, are indefinite integrals, or we just call them integrals, where there's just kind of the area under the curve for the whole thing, or antiderivatives. But the idea is here, as long as our function is continuous over the interval from a to b, then we can figure out what this is versus doing that whole big crazy limit of a summation thing. We can find the antiderivative of this function, evaluated at b, the upper limit, and subtract from that value the antiderivative evaluated at the lower limit. So it looks like this. Sometimes we write it like this just to kind of make that a little easier. So let's see if we can go ahead and figure this out. First off, my function is like -1/2 x squared plus 5. So let's go ahead and figure out what big F of x is. So it's going to be x cubed over 3 times the -1/2. And then plus 5, and then x raised to 1 more over 1 plus some constant, which is going to be x cubed over -6. So I'm going to write that. I remember the negative, so 2 times 3 is 6, and I'll just put the negative on the bottom. It could go on the top, on the bottom, or out in front, either one. And then it's going to be plus 5x plus some constant, and we're evaluating that from 0 up to 4. So I'm going to go ahead and change colors here. The function evaluated at 4 minus the function evaluated at 0 would equal to 4 cubed over -6 plus 5 times 4 plus some constant that I don't know what it is, and subtract from that the thing evaluated at 0, so 0 cubed over -6 plus 5 times 0 plus some constant. That's going to give me 64 over -6 plus 20 plus some constant minus everything in here, which is 0 plus 0 plus c. So really what that would just come out to be is minus the c. Notice here I have a plus c and a minus c, so those two together go to 0. So I just have to figure out what 64 over -6 plus 20 is. That is going to be, let's just say -64 over 6 plus 120 over 6. Multiplying this by 6 over 6 gives me the 120. So 120 minus 64 is going to give me 56 over 6, which reduces to 28 over 3. It's also approximately 9.3 repeating, or 9 1/3. So either one of those. Let's do one more of those so we can kind of get the hang of that a little bit better. So again, we're going to integrate each of these. So it's going to be 2 times x cubed over 3 plus 8x squared over 2 plus 3x to the first over 1 plus some c evaluated from -4 up to -1. This is going to equal to 2, sorry, so I'm plugging -1 in here. So -1 cubed comes out to be -1. So it's going to be -2/3. Can I just say this would reduce to being 4x squared? I'm going to say plus, and if I plug -1 to x squared, it comes to be positive, so plus 4 over 1. And then minus 3 over 1. Plus some constant. Minus with -4 into each of those. This will be a little bit more tricky. But -4 cubed gives me -64 times 2 would give me -128 over 3 plus 4 times 4 squared. 4 squared would give me 16, so it's going to give me 64. And then 3 times -4 is going to be minus 12 plus some constant. Over here, this is going to give me -2/3 plus 1. Or really, instead of plus 1, I'm going to say 3 over 3 plus some constant minus -128 over 3 plus 192 over 3. I just multiplied 64 times 3 to get the 192 because I'm trying to get the same denominator here. And then I'm going to say minus 36 over 3 plus some constant. So me 1/3 plus a constant over here. Then I'm going to subtract. If I combine the -128, the 192, and the -36 altogether, I get 28 over 3 plus some constant. This is going to be 1/3 minus 28/3 plus a c minus a c, and notice those c's go to 0. So it's going to give me -27 over 3, which is equal to -9. Please let me know how I can help you, and I will be happy to help you. Good luck, guys.